Blackboard yet, but that's because I just wrote it on Friday afternoon, but I'll get it put in there ASAP. So we're going to start with adding more definitions to stuff that we like so that we can do more proofs. You'll have this on your paper so we don't have to wait, right? We can read this definition. That a number R is rational. It's a real number. It's rational if there exist integers A and B such that R is equal to A over B and B is not 0. So you have to be able to write it as the ratio of two integers. That's what the whole rational root is there. Why is this not turning on? Is it doing anything or is it just red? Blue now. It's irrational if you can't do that. So if you can't write it as the ratio of two integers where the bottom one isn't 0, then it is irrational. So, do you believe that 10/3 is rational?
Yes.
Why? Yeah, both 10 and 3 are integers, and 3 is not 0. Okie dokie. Next up. Oh, there it is. Good. Next up, we have -5 over 39. Do you believe that that is rational? Yes. You have both -5, say, and 39 are integers, and 39 is not equal to 0. What about 0.281? Yes, this can be written as 281 over 1,000, right? And both 281 and 1,000 are integers. And 1,000 doesn't equal 0. Is 7 rational?
Yes.
Why?
Right.
That's not a 7. That was weird. 7 over 1. 7 and 1 are both integers, and 1 is not equal to 0. How about 0? Yes, we can write 0 over anything. 0 and n are integers, and we can make n not be 0. Is pi rational? That's a no. Pi is a decimal that doesn't end, right? So we can't write it as a fraction. All right, other questions or comments? You got the definition of rational. Can we write a proof? We're going to prove that every integer is a rational number. So we want to be able to show that you can write any integer. So let's do some scratch work. We're going to let n be any integer. Can we show, we want to show that n is equal to an integer over an integer where this one isn't 0. How would we do that?
Just write anything as the n over 1.
Yeah, so n is equal to n over 1. Both n and 1 are integers, and 1 isn't 0. And that's all we need to do. Okay, so I'm going to write this proof. I'm going to let n be any integer. Notice n is the same thing as n over 1. Now, 1 and n are integers, and 1 is not equal to 0. Thus, n over 1 is rational. we have shown any integer is rational. Any questions about that so far? No? Okay. Take 3 or 4 minutes and try number 2. Somebody want to volunteer? Jania's gonna do it. You what?
I didn't get far, so I wasn't sure, like, if what I was doing was just circular or anything.
Okay. Did you? Oh gosh. Did you do any scratch work?
Yes, that's, I finished my scratch paper.
Okay. What do you have there?
So first I had A and B are.
So you want to start with 2 rational numbers, yeah? So maybe X and Y. So they would be, since they're rational, they will look like this. where A, B, C, and D, and Z, where both B and D are not 0. And what do we want to show? Yeah. So to make it fit the definition, we want to show that when we add these two rational ones that are given by their definition, then we get another rational thing. So we get another integer over an integer where the bottom one is not 0. Does that make sense? Okay. And if we do x plus y, we get a over b plus c over d. Getting a common denominator, I believe that this looks like this. A d plus cb over bd. Yes? No, maybe. Then I know that AD plus CB and BD are integers because integers are closed under addition and multiplication. So I know those are all integers. I also know that BD isn't 0 because neither B nor D is 0. Right, so we assumed that X and Y are rational. That means that they can be written as the ratio of two integers where the bottom one isn't 0. So I know that neither B nor D is 0. And so B times D can't be 0, but it is an integer. So I have an integer over an integer over a non-zero integer, which makes the thing rational. Yeah.
I had my two integers, and I just put them both over 1. And I said 1 is an integer. We can't do that. And then I added them, and I had like m plus n all over 1. And I said 1 cannot be 0.
That's exactly what I did.
But your top's not an integer. I mean, it is because but you showed that the sum of every integer is also an integer. The sum of every two integers is an integer. You assumed m and n were integers or rationals.
Two rational numbers.
Yeah, so what you have then on top is a over b plus c over d over 1. So you've assumed the thing you're trying to show, right? Because you said then, well, this is an integer and this is an integer not equal to 0. But you didn't actually show this thing at any point. You just wrote it in a different way, but assumed it again.
I got you. That makes sense.
Emily, does that make sense to you? I mean, you may have it written like this, but those things are rational, right? M and N, or whatever you used, X and Y. Those are rational, so they are the ratio, or could be the ratio of two integers, right? So that's what's actually sitting there, and that's the thing you need to prove.
Gotcha. Okay.
Yep. So to do the proof, we're going to let X and Y be rational numbers or M and N, whatever you have chosen. And then you're going to say by definition, or you're going to just say the thing, I don't know, with some other transitional phrase. By definition, X is equal to A over B, and Y is C over D for some integers A, B, C, and D with B, D not equal to 0. Not B times D, but B comma D. Corey, number 10 on the back of that homework, which is going to be due on Monday, that should have N in Z. It doesn't have the element of at the very beginning of the thing. It's N in Z.
Yes, ma'am.
Okay, by definition, X is A over B, Y is C over D for some integers A, B, C, and D with B and D not equal to 0. Okay, we good? And then I would say something like consider or notice, observe, looky here. X plus Y is equal to A over B plus C over D. which is equal to AD plus BC over BD. Now, AD plus BC and BD are integers, and BD does not equal 0. Thus, x plus y is rational whenever x and y are rational. So you know how when we did like even and odd, we said like this is an integer, therefore, you know, this thing is even, right? It's 2 times an integer, and we had to say like this fits the definition is basically what you're saying. For a thing to fit the definition of rational, you need top and bottom to be integers and the bottom to not be 0. And so just, I don't know, that's necessary every time to say. It's like top and bottom are integers, bottom's not 0. And if it's not obvious, like in this case, I think it's obvious why I should not say that, because what if it's not?
How can we assume that BD does not equal 0?
Yes, maybe it's not obvious. That's what I was just saying. Because B and D are not 0, and so their product can't be 0. Right? The assumption is that because these are defined as rational, these things are not 0, either of them. And since neither of them is 0, then the product's not 0. That's the 0 product property, I guess, in reverse there. What are your thoughts? Is this okay or not okay? Okay. Okay, do number 3 then now. And then we'll have a volunteer dictate it. Narrate, dictate, speak it into being. Emily, did you go to the Sweet Tea Festival?
I did. I went. My dad last minute came to visit me this weekend, and we didn't actually try any sweet tea because I don't know, the flavors were weird.
And you didn't want to go for it.
No.
But did you have fun at the festival?
It was nice. I went and visited where I work, and they were really aggravated that I showed up because they were really busy.
But they were.
Yeah. I was like, I'll get back there and make it myself if you guys want.
I just order the most complicated drink and then go. Go blend this for me, please. I just plop my knuckles right on top of my iPad. Eunice is gonna love that when she watches this back later. We'll see if she comments on it, and then we'll know if she's watching them or not. Yeah, I normally have a cheat sheet for myself of things to refer to when, like, if I get stuck. I don't have that today. This might get weird. I won't get stuck. Yet. Yeah, this is fine. Yes. Brian, I am ready, but I don't know if your classmates are. Yeah. Just keep standing. Here, I'll keep standing. You keep sitting. Michael, did you go to the Masters this year?
No, my parents went and they were like, hey, I went to the Masters, you didn't get your hat. I was like, no, thanks.
Yeah, it's nice. They got you something, yeah.
Yeah, it's true. I asked for the hat and they were like, okay, we'll get it. I'm planning on going next year. So.
Okay.
Oh, we'll see.
I live right next to them.
Oh, yeah, you do.
I'm from 18.
Oh. We'll go to school.
You're from?
Yeah.
Small world. Janai, are you all right? Are you all right?
Oh,
Yes. Mm-mm.
Oh.
You look disgusted that they were from Aiken and Augusta.
Literally the worst.
Oh,
I was just thinking, I was trying to think in my head, Aiken and Augusta are both in Georgia.
Augusta's
Aiken's in
Georgia.
South Carolina.
Oh,
It's like
Yeah.
Augusta's Georgia, Aiken's South Carolina. 'Cause I was like,
But
I
they're
know
like-
that Augusta's in South
That does make sense why you were making that face, though.
Carolina.
Aiken's like on the border. You could walk 2 steps.
Do your parents like rent out your house for the masters?
They did it twice. It wasn't bad. We went over to a grandpa's house
Yeah.
because it lines up with the school's spring break.
Right.
So
Smart.
it was smart.
Pay for the spring break trip if you wanted.
Yeah, spring break to the grandpa's house.
Well, I mean, it could have been a more exciting trip, but
They give us windows.
you could pay for the Wendy's. Frosties for everyone.
We went on a trip in the summer. So.
We are gonna do this, Brian. You ready? Are you gonna do scratch work? You can jump in.
I mean, I can jump in if you want.
Let's jump in. Wait, do y'all want him to do scratch work? Let's do scratch work, Brian. I changed my mind.
So we have N and M are rational. Where N equals A divided by B, and M is C divided by D, where A, B, C, and D are rational, and B and D are not 0.
They're integers is what you mean, but yes. Uh-huh.
And we need to show that N times M is equal to an integer over another integer that is not 0.
Okay.
So, I guess proof.
Yep.
Let N and M be rational numbers. By definition, N equals A divided by B, and M is equal to C divided by D, where A, B, C, and D are integers.
Sorry, I'm just so distracted by your M and N being in the wrong order that I cannot. I'm just so distraught about that I'm having trouble listening. Do you notice that they're in the wrong order? And every time you say one of them, I'm like, what?
We can switch them.
No, I can't now. Okay, I'm with you, I think.
Okay, yeah. Notice that M times N is equal to A times C over B times D. Now, since AC and BD are integers, and BD is not 0, M times N is rational when M and N are rational.
Oh gosh, I did do it out of order there too. What was that?
M times N is rational when M and N are rational.
What do we think?
Make sure to get the right letters.
That was a lot. Do you have questions about that? Does that make sense?
Yes.
Yes, makes sense. Good. More definitions. Okay, so we're not gonna like divide outright. Sorry. Excuse me. I'm tired. We're not gonna do like outright division because the integers aren't closed under division. So we're gonna just, whatever. But we're gonna talk about divides, and this is really talking about multiples of things, and if a thing does divide into something evenly. Does that make sense? So if n and d are integers, d is not 0, then d divides n if there's an integer k such that n equals d times k. This notation, y'all, is kind of strange. This would be brand new probably, is that d divides n. And that is like the opposite. That's saying like this thing, that n over d is an integer. Does that make sense? It's like backwards from what it looks, because we're used to doing this sort of thing, which is the wrong order for how this works. You get what I'm saying? So this is like a sort of a mind trick. You gotta get used to it. That this is that n is a multiple of d. So the bigger one, that n is bigger. That's the thing on the right side. That n is the bigger one. So d divides n if there exists an integer k where n is equal to d times k. So what we're going to do right now is try to like play with that definition and see if that makes any sense to us, okay? So does 3 divide 12? Think about this. Does 3 divide into 12 evenly? And the answer is yes. You can write 12 as 3 times 4, and 4 is an integer, so we're good to go. Does 1 divide 16? Does 1 divide evenly into 16? Yes. Yeah, you can do 16 is 1 times 16, and that's an integer, so we're good to go. Does 12 divide evenly into 4? And the answer is no. There, 4 would be 12 times a third. That's a half, sorry. This would not be an integer. Oh my. Oh gosh. Things got really rough there. 12 times 1/3. This is not an integer, so this thing would not be true. How about negative 16? Does negative 16 divide 32? Does negative 16 divide into 32? The answer is yes. 32 is negative 16 times negative 2. And that is an integer, so we are good to go. Definition of divides makes sense. You can write the thing on the left is a divisor, right? It works as a divisor, an even divisor of the thing. Okay, so let's practice some more with some abstractness added to it. Instead of having 2 numbers, now we're going to have 1. For what integers is it true that a divides 1? Yeah, 1 and then also negative 1 would work. So 1 and negative 1, we would like to write 1 is equal to a times something. If a was 1, then we can make this 1, and if a is negative 1, we make this negative 1. For what integers is it true that 1 divides b, that 1 divides into b? All of them except for 0, yeah. All integers b except for 0. Is this making sense? Yes? So far? For what integers a is it true that a divides into 0? 0 into 0 would be bad. I think it's none. Because you want to be able to write 0 is equal to a times an integer, right? But the thing up here says D can't be 0. That would work, but D can't be 0. So we got nothing. I think. That's my opinion. What do y'all think? What about, yeah, that's the same thing. Oh, crap. I wrote down any A.
Would it make sense because if you have any integer, if you think of it as division, like 0 over something else, it would always be 0. 0 is an integer.
So it would be anything
Yes,
Yes.
except for 0.
except for 0.
So I don't know if this is intentional. So you wrote, and I assume you're referring to the equation of the top, but so in our equation, a dash 0, right? 0 would take the spot of D, but in the top equation, you're plugging 0 in for the value for n instead of D. I don't know if I'm misinterpreting that.
On 2 or 3?
For 3.
This should be D divides into N. So the N is 0. Huh?
Is 0 an integer?
Yeah.
That means-
Then it could work for any A, right? Yeah. I don't think I have the order backwards though. But I do think it is all of them. Because here we want, here, if we had 0 in here, this is fine, right?
And that's K and not D.
Right. The D not being 0 would be down here, right? Okay, so we would let K, the integer K would be 0 for everything. So all A will work. Yes or no?
Yes.
I think so. And then 4 would be none because D can't be 0 by the definition of the divides thing. Yes?
Yes.
Okay, how many integers do you know that can divide into 3? 1, 3, -1, -3. Yeah? How about 5 integers where where 3 divides B? 3 works. 6 works. 9, 12, 15. Sweet. Yeah, I was only supposed to list 5, Janaya.
I started at 6. I don't know why.
Oh, well, then you should list 18. Go ahead and do that. What do y'all think? Are we doing okay? Yes?
Yes.
We have this theorem. A, B, and C are integers. A is not 0. These 3 things are true. If A divides B and A divides C, then A divides B plus C. If A divides B and then A divides B times C for all C. Theorem part 3 there. If A divides B and B divides C, then A divides C. You've got a transitivity property and associative property, sort of, and I don't know, commutative. Anyway, you're trying to pick up some properties here with with divides. Part 1 of this you're going to do for your homework. We're going to do part 2 and part 3. Cool? I don't remember what number it is on your homework, but it's there. number 9. Number 9. So, okay, part 2 though, our claim here, the statement is that if A divides B, then A divides B times C for all C. Okay. What do we get to assume?
B is not 0.
We get to assume that A divides B. We get to assume that A, B, and C are integers. And what's not 0? A? I think it's A.
Oh, yeah.
Okay. So we get to assume that A divides B. What are we trying to show? That A divides B times C. What does it mean for A to divide B times C? Divides into it, right? So we're going to say that we could write BC as A times an integer. And that's the thing we're trying to figure out. Okay, so what do we get to assume from the fact that A divides B? Yes, that B is bigger. So how do we write that with the equation? That B is equal to what? What's the definition of divides? Go back to that, look at it. A divides B if what?
It equals.
Yeah, A times K. A times some integer K. Is that okay? That's the definition of divides. It divides evenly into it. That number of times it divides evenly into it is K. Okay, so B is equal to A times K. We want to look at B times C. Well, that would be A times K times C. You good with that? Because B is AK. And then that you can write, like this. This thing is an integer. Oh, no, don't do that. That's not the point. That's not the point. There we go. And that is an integer. And so we're done. What do we think? Yes or no? Okay, tracking. Good. Proof. Let A, B, and C be integers and A not 0. And then we're going to say what we get to do, which is to assume that A divides B. I'm going to say something like by definition, or then, by definition, B is equal to A times K for some integer K. And we're going to say consider B times C, which is equal to A times K times C, which is equal to A times KC. We're going to say since KC is an integer, A divides B times C. Thus, A divides BC whenever A divides B. Thoughts? This is okay?
Yes.
Okay. We're going to keep going then. You good with that? Alrighty. I know we got a lot of space here. Sorry. I didn't realize how quick that proof will go. I got to write this down. By that, I mean copy and paste it onto my paper. All right, so this is the thing that we're trying to prove. If A divides B and B divides C, then A divides C. This is the transitive property for divides. What do we get to assume if A divides B? Or since A divides B, what do we get from that?
A times K for some integer.
Okay. What about B dividing C? What do we get from that? Use a different integer, but yeah. So C is equal to B times L for some integer L. And what are we trying to show? Yeah, we want to show that A divides C, and what does that mean?
C equals A.
C is going to equal A times some integer. So we have that C is B times L. What else do I have? Yeah, B is AK, so this is AKL, which is AKL. And that thing is an integer, so we're done. And going back to the very beginning with this, in that theorem, it said to let A, B, and C be integers with A not equal to 0. I'm going to say assume A divides B and B divides C. Then B is equal to A times K and C is equal to B times L for some integers K and L. I'm going to say something like, notice C is equal to B times L, which is equal to A times K times L, which is A times KL. Since KL is an integer, A divides C whenever, no, I'm not going to say that there. That's going to be really gross. Thus, if A divides B and B divides C, then A divides C. Thoughts? Thoughts? No thoughts? Thoughts are fine. We're working. We're cooking. Guys, we're moving. We are moving. Good. Hello. Alrighty. So we are in the middle of page 5 then. And we have this another definition for prime. It's just sort of restating this. An integer p greater than 1 is prime if the only positive factors of p are 1 and p. So the only positive divisors are 1 and p. So you can't use the divides thing with anything except for 1 and p. Yeah, okay. It is composite if there is if that's not true. So if there is an integer between 1 and n where a divides n. So for example, 9 is not prime because 3 divides into 9 evenly. Good? Okay, the fundamental theorem of arithmetic says that every integer n can be written uniquely as a product of powers of primes in increasing order. You can see those primes, well, you can see some examples done here. Number 1 is the number 2, which is 2 to the first. And then we have 3, which is 3 to the first. 4, which is 2 squared. 5 is 5 to the first. 6 is 2 times 3. Those are the prime factors to their powers. 7 is prime, so it's just one factor of 7. 8 is 2 cubed. 9 is 3 squared. 10 is 2 to the first, and then 5 to the first. 11 is prime. 12 is 2 squared, which is 4 times 3 to the first. And then 13 is prime. The fact that you can do this, writing out every number as a product of primes, helps you do a lot of proofs with things about primes. But yeah, anyway, that's the fundamental theorem of arithmetic. Kind of fun, no? Yeah, right. 13 does equal 13, though. But also 13 to the first. So that is all of 4.3 and 4.4. That's homework 1. Is 5. This is homework 5. Homework 1 from test 2. That homework 5 is over 4.3 and 4.4. So, as I said, you shall be able to do all of it now. I mean, not right now. But after class today, you should be able to do all of it. And so come Friday with questions about it. Be ready to turn it in to me on Monday. Cool. Any questions about that? Eunice, on number 10, it's missing a Z. Okay. I fixed it now, but I did not fix it before I printed it. Okay. Yeah. Let's do the quotient remainder theorem. So, fundamental theorem of arithmetic, boy, is that one. FTA, because I won't ever write arithmetic down because I cannot spell it. Maybe I can, actually, now that I think about it. The quotient remainder theorem is this one. This is kind of fun. N is an integer. D is a positive integer. There are unique integers Q and R, quotient and remainder. There you go. R is between 0 and D. Could be 0. Can't be D. Such that N is equal to D times Q plus R. Is that every number with a particular divisor has a quotient and a remainder. This makes sense. If D divides N, then N is equal to D times Q and R is 0. Does that make sense? There would be no remainder. So this is another way to talk about division without actually dividing, because dividing introduces trouble. But you can see here, like this is regular division, this thing, and divided by D or whatever would give you A over D, and then is the quotient plus the remainder over the divisor, right? Divide 33 by 8. What happens? What's 33 divided by 8? Yeah, you would do this, you get 32, and that's 1, so it's 4 and 1/8. There's like really a plus sign in here, right? It's your quotient plus your remainder. This is 33 divided by 8 is 4 plus 1/8. You see how that's like, this is the definition of division. I mean, this is division, but just doing it a little bit differently. Yeah? Okay, so we have N is the dividend, D is the divisor, Q is the quotient, R is our remainder. R is the remainder when A is divided by D, or when N is divided by D. We're going to do this. We're going to write each of these in this form up here. So N is equal to D times Q plus R. And remember the allowed values of R are that remainder is specifically between 0 and the divisor. Because if it was more than the divisor, what would happen? The quotient, yes. That quotient would increase and the remainder would get smaller. Yeah, okay. Alrighty. So we're going to do 52 divided by 8. So 50, that's a highlighter. Let's not write with that. 52 is equal to 8 times a thing plus a remainder. 6 and 4. So the R value is 4. Negative 26 divided by 3. So we're going to have negative 26 is 3 times a thing plus a remainder. That would be 18. Okay, so if we did negative 8, that's negative 24, right? And I would need to make this a negative 2. That's not in the rules. What does my remainder have to be? It needs to be positive between 0 and 3. Okay, so if I'm not going to go to negative 8, what should I go to? Yeah, so if we go to negative 9, then we get to add 1, and that remainder is in the right range. Yeah, it is. Does that make sense or no? Okay. 79 divided by 5. We have 79 is equal to 5 times 25 plus 4. Yes, it should be. Good. 5 times 25 is 125. 5 times 15 is better. But that's still 75, so the remainder is still 4. Because I am good at this. Sort of. Alrighty. 789 divided by 23. We have no hope of me doing this in my brain. So 789 is 23 times a thing plus a remainder. That remainder should be between 0 and 23. 34. 34. And the remainder is 7. 34 I did from memory because I did this yesterday. I prepped it yesterday. Do you know that I think yesterday I also wrote down that 5 times 25 was 75? I'm going to have to go look at that. Like I said, I didn't bring it with me, so we won't be able to know. But I think I did. We can look. We can look on here. Awkward. Let's fix that. Look, there's a 34 and a 7, though. Way to go, Corey. You don't even have a calculator. Well, I know, but you were still doing it without your calculator. Doing it on paper or in your head? Okay, well, I'm less impressed now, but still impressed. Okay, so the remainder there is 7. The thing, like I said just a second ago, it's okay that I can't actually multiply because we care about the remainder, and I did get the remainder right. The remainder is the thing that we're really worried about. And when we do that, we talk about that as modular. It's modular arithmetic stuff. So R is the remainder mod D. You've used this before. Most of you computer science people certainly have. The rest of us maybe not. But so this one would be that 4, the remainder is equal to 52 mod 8. It's how many are left over or how many to get to the nearest multiple. So 52 is 4 off from a multiple of 8. 26 is, or negative 26 is 1 off from a multiple of 3. So the remainder is 1 when you do negative 26 mod 3. On the 79 one, we've got 4 is our remainder when we do 79 mod 5. How many off of a multiple of 5? And this is the other reason why that R value is stuck between 0 and whatever the divisor is. Because if the remainder was 5 here, then it would be, right, it would be 0, right? Okay. That would be equivalent to being 0. Whatever. That got weird. But y'all got it. 789 divided by 23. The remainder here is 7. And so that is 789 mod 23 is 7. If we go back and look at any of this other stuff that we did today, up here, where is it that I want to go? So if, let's go back up to the divides definition. If this is true, what is the remainder? What's the mod thing? So what is n mod d? It's 0, yeah. Because n is a multiple of d. So there's no, it's already sitting on a multiple. We don't need to get to the closest one. Also, that goes back to this thing. Your R is 0 there. So it would be 0 mod d. What is going on with these guys? Mod 3, right? When you're moving by 3s, you have no remainder mod 3. Well, when you're moving by 3s, whatever your remainder is to start with stays your remainder, right? So if we were talking about 4, 7, 10, 13, 16, what are all of these mod 3? What's the remainder mod 3 of each of these? How far off of a multiple of 3 are each of these? All 1 off, right? Because we started by 1 off and we moved by 3 for each of them, right? Does that make sense? Yes? Does it? Why are you laughing?
Oh, no, I was thinking about a simpler way to do the 789, but when I did it in my head, I realized that it was more than just division.
I love it when that happens. Sometimes I'm like, oh, I got a really good way to teach this. And then I start doing it. I'm like, this is not a really good way to teach this. How do I back out of it? I don't know. We just follow through. We're stuck now. That's good. Okay. R is the remainder divided by, when n is divided by d, 789 divided by 23. The quotient was 34. And the remainder is 7. All right. Y'all, we are moving. We're doing so good. Let's suppose that we're using a 12-hour clock. We're not distinguishing between AM and PM, and the current time is 1 o'clock. What time is it going to be 4 hours from right now? Good, everyone. You know how to read that clock. Okay, 5 o'clock. What about 16 hours from right now? What about 28 hours from right now? It is also 5 o'clock. Why? Yeah, it's a mod 4. Well, it's a mod 12, but we're also doing mod 4 because we're starting over every 12 because it's a clock, right? And then we're looking for a remainder of 4, mod 12. Yes? This is the remainder. We want these numbers, whatever they are, to have a remainder of 4, mod 12. Yes? No. Should it be 5?
I was thinking about, like, but then there's no 0, but you
I know. That maybe doesn't work very good for a clock. Because the 0 is 12, which would make it mod 12, and that's good, but we want to go from 1, and that's 0. We got a combined mod 4, mod 1 and mod 12 happening.
What's mod 1?
Nothing. That's not real.
It makes sense though, like, if you go by mod 12, you just put all the numbers on the clock, it makes sense.
Yes.
You try to think outside the clock.
Right. You're right. The mod 12 thing is necessary, but the fact that we also are starting at 1 o'clock and moving, and that makes the writing that down ugly, shall we say. What are some other numbers that would be 5 o'clock also? 40, 52, 64. And Jacob, what are you doing for each of those? Moving by 12, because that's the same as doing nothing, right? Yeah? Think about coterminal angles, right? Do a full rotation, you're in the same spot, because you're looking at mod 2 pi for radians. The remainder mod 2 pi puts you wherever you are. Okay. Suppose today is Tuesday. It isn't, but let's suppose that it is. Normally I teach this probably on a Tuesday. There's 50 shot, but whatever. Try to do that math. You can't. That doesn't make sense. It's fine. If today was Tuesday, what day of the week would it be a year from today? It would be Wednesday. Why? Do you know why that is? Why? Well, yeah. 365 mod 7 is 1, or you can think about 365 is 52. I can't do this in my brain. Am I doing the right thing? What's that number? Or is it supposed to be 7? It's supposed to be 7 times 52 plus 1. Yes? Yes?
Yes.
Good, good, good. I don't want to do this anymore. We have to. It's fine. What happens if we have a hurricane next week? We should keep going.
Yes.
Yes. A while back, I told you, like maybe 2 weeks ago, I told you every integer is either even or odd. And right now, we're going to prove it. But we have to use the quotient remainder theorem, which is why we weren't quite ready to prove it then. Also, we didn't know what even and odd even was, did we? No. But now we do. And now we're going to prove this with the quotient remainder theorem. We're going to do some scratch work because I haven't looked at this theorem, this proof in a year. I meant to do that today before I walked in here, but I didn't. It's going to be fine. Right?
Yes.
So, we're going to do some scratch work. This is how things would work for you, right? We're going to assume n is any integer. So by the quotient remainder theorem, we can write n is 2 times something plus a remainder. Right?
Right.
We can choose any divisor. Quotient remainder theorem is way up here. That n is an integer, d is a positive integer. So n we have let be anything, any integer. D we have chosen to be 2. Okay? Then there are unique integers q and r, such that n is equal to d times q plus r. So if we have chosen d to be 2, if we have chosen, let me try that again. If we have chosen d to be 2, what do we know? R is either 0 or 1. Because r is also an integer that is greater than or equal to 0 but less than 2. Right? Y'all. So r is equal to 0 or r is equal to 1. Do you see what's going to happen if r is 0? N is, and if r is 1, n is odd. That's the proof. Right?
Right.
That's good, yes? Let's write it up. Proof. This is how my scratch work goes normally, y'all. It's just sort of like a, where am I going? How do I get on this road? And then once I'm on the road, I stop. Okay, proof. We're going to let n be any integer. By the quotient remainder theorem, we have n is equal to 2q plus r for some unique integers r and q. Further, r is equal to 0 or r is equal to 1. I'll tell you what this is in just a moment. Let r equal 0. Then n is equal to 2q. Since q is an integer, n is even. Case 2, we are going to let r equal 1. Then n is equal to 2q plus 1. Since q is an integer, n is odd. Therefore, every integer is either even or odd. Cool, huh? Now, y'all, that right there is called a proof by cases. Notice how we followed a theme to a place where we had two options. And then we did little mini proofs with each one of those options. That's called a proof by cases. So, oh yeah, A and B have the same parity when they have the same remainder mod too. But like something like this, given any two consecutive integers, one is even and the other is odd. So something like this, you're going to start chasing that rabbit, right? Do what you get to assume, and then you're going to see two choices. And when you see those two choices, we're going to break into proofs by cases, which is just two proofs in one proof. I don't know what time it is, but y'all are all packing up. I have 3 more minutes. I could probably write this whole proof. Let's not. Y'all have a good day. I'll see you on Friday. Come with questions on Friday for homework 5. Yes?